screen, my video.
Okay.
Let everybody in.
I'll get the presentation back.
Oh, if you wanted people to see your face before you put the presentation, you're certainly.
Oh, all right.
That's up to you.
Well, I'm not sure where I can see the participants here.
There is a list where you can stroll through. It depends how you set up your view. So, well, I'm going to welcome people. Let me see if I'm recording here. Yep, so we're recording. I am happy to have Gleb coming in from Switzerland late at night. He's not flopping around too much, and we'll welcome his talk. Next week, we'll have Raphael Zettner speaking and keep this going. Turn off my video.
Just a second. Okay, so can you see the presentation?
Yes.
Okay. So thanks everyone for attending. The talk is about diffeomorphism groups and some algebraic geometry constructions. And the main result we'll prove is that the group of diffeomorphisms of the product of two spheres is not simply connected. And the same result holds for many other algebraic surfaces. For instance, hypersurfaces in CP3, where degree is neither 1 nor 4. But we'll stick to the case of S2 times S2, so for D equals 2, because this is, in this case, B2 plus is 1, and it makes the case a little bit more complicated. So the talk itself will consist of two parts. The first part is the construction of non-trivial elements in pi1 of diff. It's based on some codimension to surgery introduced by Michael Atiam. And you can read it in his seminal paper on analytic surfaces with double points. And the second part is prove that the constructed loop is not contractible. And this part is gauge theoretic and based on two papers. First is by Daniel Ruberman, where an idea that gauge theory can be used to say something about diffeomorphism groups has been implemented. He found some exotic diffeomorphisms, which are topologically trivial, but not smoothly so. And another paper is by Peter Kronheimer, and it contains a specific construction, some symplectic families, families of symplectic manifolds, which we'll be constantly using. We'll modify his construction a bit, but essentially it's due to him. So before we study algebraic surfaces, let's look at the simpler case. Let's look at two-dimensional sphere, and we prove now partially a result of Smale about homotopies of diffeomorphism group of S2. We will prove that the group is not simply connected. So let's consider a product of unit complex disk and CP1. We call the product Y1. It is a trivial bundle over both CP1 and disk, and I want to think about it as a bundle over disk. And as the bundle is trivial, it has a trivialization. So by trivialization, I mean a family of maps from CP1 to Y1, so that each map is an inclusion of inclusion of CP1 to some fiber of Y. So, well, it's given by this formula. So phi t is a family of maps. Now we pick a point in Y1 at central fiber and blow up Y1 at this point, and we get another surface called Z. And this surface contains a pair of -1 curves, exceptional curves. So the first one is the exceptional divisor. We call it E1. And the second one is a strict transform of the central fiber. Proper transform of the central fiber. Now, with these exceptional curves, we can associate contraction maps. So the first contraction map, C1 contracts E1 and C2 contracts the other curve. So we have two maps from Z to Y1 and to Y2. So C2 is a map from Z to Y2. Now look at the diagram at the bottom of the page. So the arrow in the middle is C1 inverse. Well, the arrow is dashed to indicate that this map is not a map, it's a birational map. So it's defined over the complement to some codimension 2 subset. But it defined over the boundary of delta. So on the fibers that lie over the boundary. And therefore, we can compose phi t with C1 inverse and then C2. So this way we can get a map from CP1 to Y2. And all the maps I mentioned commute with the projection with pi. Okay, so let's compose phi with C1 and C2, and we get another family of maps. We call it Psi. So CT is a family of maps from CP1 to Y2, and it gives you trivialization for the bundle Y2 over the boundary. And you can ask if this trivialization extends to be a trivialization over the whole disk delta. So phi t was defined to be extendable, was defined to be a trivialization for the whole bundle. But psi t is not extendable. Otherwise, you would prove that CP1 times CP1 is diffeomorphic to a blow-up of CP2. So blow-up of CP2 is a twisted S2 bundle over S2. It has non-trivial Stiefel class, and it's not diffeomorphic to the trivial bundle. Well, this is because you can place Y1 in S2 times S2. You can place a bundle over the disk to be a bundle over to be a piece of bundle of S2 bundle over S2. And when you do this blow up and contraction thing, you will get a different complex surface. You will get the blow up of S2. So this way we constructed a trivialization of S2 bundle over the disk, a trivialization over the boundary which does not extend to be a trivialization over the whole disk, and that gives you a loop in the group of diffeomorphisms. So, and homotopy classes of such non-extendable trivializations, they are one-to-one with Y1 of diff of the fiber. And now we will do the same thing, almost the same thing for surfaces. And again, I mentioned that the surgery, the analog of the blow-up we did before, is described in Atya's paper, and it's also described in a paper of Miles Reed with many generalizations, with many other plops, which probably also lead to some loops in the group of diffeomorphisms, but that's to be checked. Okay, so let us consider a holomorphic fiber bundle, Y1, over the unit disk, with a fiber being an algebraic surface. So let's, for instance, keep in mind, think of CP1 times CP1. And we assume that the central fiber of our holomorphic bundle contains a smooth rational curve of self-intersection -2, and moreover, we want the normal bundle to this curve inside the threefold Y1 to be of certain splitting type, to be biholomorphic to O-1 plus O-1. We later we will discuss how to construct many such examples. Now let's assume that we have one such bundle. And we denote this sphere, this rational curve by E1. So now we blow up Y1 along E1 to get a threefold. And in this case, the exceptional divisor is CP1 times CP1. Well, an exceptional divisor is a root surface, and it should be the projectivization for the normal bundle of a curve along which you do the blow up. Now our normal bundle is O-1 plus O-1, and it has the trivial projectivization. So what you get is CP1 times CP1. So the exceptional divisor carries two rulings, two holomorphic fibrations by CP1s. The first that comes from our blow up, and the other one is by spheres in different gamology class, in the other gamology class. And we can do two different contractions. So we can contract the original ruling, and it gives you a map from Z to Y1. We'll call it C1. And C1 sends the exceptional divisor, CP1 times CP1, to our curve E1. And if we contract the other ruling, we again get some threefold, Y2, with another rational curve, and as a CP1. So these two copies of CP1, are our four-dimensional analogs for E1 and E2 from our previous construction with S2, with the diffeomorphism group of S2. Okay. So let's fix some trivialization phi t for y1 and use the contractions to construct a different trivialization for y2. So again, so we have a family map. Have a family map phi from x to y1, family of inclusions. We compose it with C1 inverse, then compose it with C2 and get family of inclusions from x to y2. And we can ask the same question. So we get some trivialization and we can ask if it's extendable. And later we will prove it's not extendable, and that would give you some non-trivial loop of diffeomorphisms of X. There is another way to put it. So you can glue y1 and y2 along their boundaries, and the gluing function is composed with the contractions we introduced. And what you get is a bundle or two-dimensional sphere and fiber X. So psi, the family, a trivialization psi is extendable if and only if this bundle over S2 we'll call it W. So this bundle W is smoothly trivial. Okay, so that's how you can get some loops of diffeomorphisms. The proof that they are non-trivial will come shortly, but that's the construction. Example. So we assumed before that we have a holomorphic bundle or a unit disk, and that the central fiber contained a rational curve with specific properties. And now I would like to tell you how to get many bundles, many such bundles. And the simplest comes from pencils of hypersurfaces. So let's say take a pencil of hypersurfaces in CP3, for instance, a quadric pencil, and define V to be a threefold in the product of CP3 times delta. It's given by the question on the slides. It is a fibration over delta, which is not smooth. So the central fiber is singular. It has a quadratic singularity. And you can resolve this quadratic singularity. And when you resolve a quadratic singularity in 3 dimension, the exceptional divisor is CP1 times CP1. The exceptional divisor must be a quadric. And this quadric comes with 2 rulings. You can contract either of them, and it gives you 2 smooth threefolds, which are now smooth fibrations. So that's how you can get many bundles with desired properties from pencils of hypersurfaces. And for quadrics, it's easy to write down an explicit equation. but it applies to any degree hypersurface except CP2 and to many other kind of hyperplane sections. Okay, so now we will go to the part 2. And the strategy of our proof is we first assume that that the loop is trivial, that our trivialization psi is extendable, or in other words, that the bundle W is simply trivial. Then we will equip the fibers of W with Kähler forms. Well, it is possible, though W itself is not a symplectic manifold and it's not a complex manifold, but you can make the fibers into Kähler surfaces. Then we will define and compute family Seiberg-Witten invariants for the bundle W, and we will get some wrong numbers we shouldn't be getting, and that's how we obtain a contradiction with the triviality, with smooth triviality of W.
A quick question for number 2. When you put
Sure.
your Kähler forms on the fibers, are you literally just picking a family of these 2 forms, or are you picking a kind of global 2 form that restricts to a Kähler form on each fiber?
Well, you can do with a global 2 form, but the global 2 form will not be closed. So there will be a 2 form on W so that it restricts to each fiber as a Kähler form, but the form itself, the global form, will not be closed. But we'll get to it very soon. So maybe some questions about the construction of loops, because we're not going back to that part. It's only the proof we'll be doing. Okay. So the Kähler form, the way you can put Kähler forms on W was described by Kronheimer. So I'll just go through his construction quickly. And let's start with our example, our singular example first, with V. So V is a singular threefold. It has a quadratic singularity. V is a fibration over delta. And we can resolve V to get a threefold with the exceptional divisor CP1 times CP1, and then contract one of the rulings of CP1 times CP1 to get a new threefold Y1. That's what. So that's I think that's called small resolution. So you can replace a neighborhood of a quadratic singular point with a neighborhood of a rational curve. Yeah, that's the inverse map from Y1 to V contracts this curve to a point. And the whole V is embedded into the product of CP3 times delta. And everything commutes with the projection to delta. So all the things. Now on the product of CP3 times delta, we have a global Kähler form, which restricts to each CP3 as the Frobenius-Studi form. And since V is embedded there, we can pull back this form to V, and we call it omega. Well, omega is not, strictly speaking, a Kähler form because V itself is a singular space. but it's Kähler everywhere except this point. Now we have a contraction map from y1 to v, and we can take a pullback of omega and get a close to form on y1, which is almost everywhere Kähler, except it is degenerate along the curve E1. So now we are going to fix it. So we will perturb this form and make it Kähler at the center fiber. So now it's not Kähler at the center fiber because of the curve E1 in the center fiber. Okay. Well, since the I think it's described in the book of Griffiths and Harris that if you have a negative curve, you can always find a form supported in the neighborhood of this curve, 1-1 form, which is positive. So for -2 curve, we take such a form and perturb it. The perturbed form, we'll call it omega plus epsilon A1. This form restricts on each fiber as a Kähler form. But you see, the cogamology class of this form changes from a fiber to fiber. So the integral, for instance, over E1 in the center fiber must be positive because of the perturbation we made. But if you transport the curve E1 to the fibers nearby and compute the same integral, then you get 0, because away from the center fiber you don't have any perturbation. It's just form omega there, and it vanishes. The integral must vanish over E1 because omega region omega is globally closed. The integral of omega must be always the same for each fiber. So if you translate E1 to any other fiber, you must get the same integral. All right, there is a picture. So this sphere here is a base for the bundle W. And there is a small region near the North Pole where evaluation of my perturbed Kähler forms on E1 is positive. Then away from this small region, we have no perturbation and it's 0. And near the South Pole, you have a similar picture, but for the curve E2, for the curve that arises from the other contraction. So again, and you have a different perturbation there, A2. So Y1 and Y2 are symmetric. You can do the same. Any construction you do for Y1, you can also do for Y2. Okay, so now the fibers of W are equipped with Kähler forms. And okay, and we move on. Let's undo the writing. Okay, so we'll be computing some Seiberg-Witten invariance for W. There is some. Oh, thanks for the question. Let me yeah. You also can leave your questions in the chat box and check others' questions in the chat box. So now I'm answering a question about Kähler forms. Well, W is not a complex. Well, it's a priori is not a complex manifold. So it need not have any Kähler forms, but even so it's not complex, it is possible to equip the fibers of W with Kähler forms. The fibers are Kähler surfaces. We just equip them with Kähler forms, yes. They are algebraic. The fibers are algebraic. So what I'm doing now, I'm just constructing a continuous family of Kähler forms over W. Of course, each fiber itself has some Kähler form, but what I'm doing continuously, and also taking care of the periods of my forms over the curve E1. So the curve E1, I'm thinking of this gamology, since it is a bundle over S2. Yes, well, you can use some partition of unity argument to equip the fibers with Kähler form continuously, but I also need to do it in a way that I know the integral of my Kähler forms over the gamology class E1. So, well, actually, almost all fibers except the one on the North Pole, the one on the South Pole, are equipped with Kähler forms automatically, because you have form omega. Where you don't have Kähler form is at the North Pole fiber and the South Pole fiber. But you can do small perturbation to make them Kähler. Thank you for the question. Okay, so we will be computing some Seiberg-Witten invariants for W, but before doing this, I need to introduce exactly what kind of invariants we'll be using. So family invariants are, there is a paper by Tianjun Li and Aikul Yun, where family invariants are studied, and it's a great paper to learn about them. And so I'm not giving any introduction to Seiberg-Witten equation and some theorems from gauge theory I will be using. They all can be found in Salomon's books in geometry and Seiberg-Witten invariants with proofs. So our setting is a closed, simply connected for manifold, and we consider the Seiberg-Witten equation there. So it's a certain system of PDE with parameters, and the parameters. So I'll be using 3 parameters. The first is a discrete parameter, the spin C structure. Well, for us, for the purpose of my talk, it will be just a gamology class, a cogamology class. At least in symplectic case, since you have a canonical spin C structure, all others are parameterized by cogamology classes. So we will call the class delta. And we will also need 2 continuous parameters, a Riemannian metric and self-dual perturbation form. So self-dual for the chosen Riemannian metric. So the space of the continuous parameters form a bundle, a vector bundle over the space of Riemannian metrics. So the base is the space of Riemannian metrics, and fibers are self-dual forms. So we just pick some point in the parameter space P, and then spin C structure, and then we can solve the Seiberg-Witten equation and get some solutions. And we also will need the universal moduli space for Seiberg-Witten solutions. So it's defined as follows: for fixed spin C structure, so let's fix some delta, then fix a point in the parameter space and consider the space of solutions. If we take all the solutions for all the parameters, then what you get is space M and a map, the projection to the parameter space. And this space M is what I'll call the universal moduli space. And yes, we will, of course, take our solutions up to gauge transformations to ensure compactness. Now there is a piece of the parameter space we will remove. So we will remove those pairs of metric and perturbation form for which the harmonic part of the perturbation equals to that of the self-dual part of some curvature form related to spin structure and metric. It is some submanifolds of the parameter space. So when we remove it, what we get is a nice space. We call it P star. And there is a theorem that says that then the projection, when we restrict ourselves to P star, is a proper Fredholm map of known index. Well, if you do not remove this P ret, the reducible part, then the map is not Fredholm. And we will take delta so that the index of F is -2. So in this case, a generic point of the parameter space doesn't have a preimage, but a two-dimensional family of parameters may have some. And so this tells us how to define family invariants. So let's, for instance, take it to sphere and some map from S2 to the parameter space. We perturb that map so that the image is now transverse to the projection F. If it's transverse to the projection, then the preimage consists, the image of tau is transverse to the map F, and then the preimage of tau S2 under F consists of finitely many points. And we will count these points mod 2. So you can count them with orientations, but for the purpose of the talk, let's not do orientations, let's just count them mod 2. And that's what's called a family invariant. So this not the most general definition, but it will be enough for us. So the way we define these family invariants, they they almost always vanish. And I think it's this observation. Yeah, this observation is also due to Kronheimer. So we know from general theory that the reducible part P red is in a fine subbundle. So remember that P is a vector bundle, and the reducible part is in a fine subbundle of known dimension, like a dimension B plus 2. And the space P is contractible because it is a vector bundle over a contractible space. And then if B plus is sufficiently large, then removing the reducible part doesn't affect pi 2. So every sphere in pi star can be contracted to a point. Every sphere in P can be contracted to a point without touching the reducible part. And if so, it must have trivial family invariance. Now, if B plus equals 1, then P red divides our space into two connected components. And both these components are contractible. So if we place if the image of tau is placed in one of these components, then it's again contractible without touching the reducible part, and must have trivial family invariance. So there is exceptional case. It is when B plus equals 3. Then the reducible part has codimension 3, and you may have two-dimensional spheres which are linked with this part. That's what you have, for instance, for K3 surfaces. There is a hyper-Kähler family of K3, and it's known to have non-trivial family invariance in the sense that I define them. So that's why we exclude K3. So you still can. So the proof will not work for K3. The construction for loops works, but not the proof. Okay, so we introduced family invariance to compute to do some computations with W, and fibers of W are Kähler surfaces. And now we will need another theorem, some characterization of Seiberg-Witten invariance for Kähler surfaces. So suppose we have a Kähler surface and pick some spin structure, some cohomology class. We also need to pick some Riemannian metric, and we take the Kähler metric. And for the perturbation, we will take a large multiple of the symplectic form. And then if multiple is large enough, then Seiberg-Witten solutions up to gauge are in one-to-one correspondence with holomorphic curves in class delta. So it's easy to solve Seiberg-Witten equation on Kähler surfaces. Okay, so how apply to W? So W is a smoothly trivial bundle of Kähler surfaces. You can think of it as a family of Kähler forms, Kähler metrics on a given manifold. It's the same if your bundle is trivial. You can think of a bundle where each fiber carries some structure, or you can think of a family of structures on some abstract fiber. So the family invariants that we defined, they actually family invariants for trivial bundles. So our family is W, and our spin structure will correspond to class delta of E1. Okay, so we can check that in this case the index is exactly -2. So we expect to have finitely many solutions for W. Let's go back to the picture. How to go back to the picture? Okay. Okay. So the metrics we choose are the Kähler metrics on the fibers. Then the perturbations we choose are Kähler forms on the fibers, large multiples of them. And then to see the solutions, we just need to count holomorphic curves, right? So let's count holomorphic curves. First claim is, look, away from a small region near the North Pole, each fiber carries a symplectic form omega whose integral over E1 is 0. So we cannot have holomorphic curves for these fibers. So the only curves we may have are near the North Pole and near the South Pole. So near the North Pole, we still have no curves up to the point at the North Pole, because remember that each Kähler surface there also it carries perturbed form now. It used to carry form omega, and omega has vanishing integral over E1. So we don't have curves everywhere except maybe the fiber over the North Pole, where we know we have such a curve. It's just the way Y1 was constructed. We have a curve E1 over the fiber at the top, and E1 has self-intersection -2, so we have only one such curve, so we cannot have two. Now at the South Pole we have a curve E2, and there is some computation with this flop construction. You can perform and check that the gamology classes of E2 and E1 actually have the opposite sign. And so if you have a holomorphic curve in class E2, you cannot have a holomorphic curve in class E1. So the only curve we have lies at the fiber at the top, and it's a single curve. So we expect the family invariant to be 1. Well, of course, you need to check the transversality, but that can be done, and actually it was done by in the paper of Kronheimer. So the conclusion is W has non-trivial family invariant, and we should not have any families with non-trivial and Seiberg-Witten invariants. That's how we get a contradiction. So we constructed some families, some non-trivial family, but there is general theory says we cannot have such a family, and that's completes the proof. And there is another thing I want to mention. So I'm not proving it here, but there is a generalization of this result, which is in my preprint in arXiv. It's a simple generalization. It says that so we know that the diffeomorphism group is not simply connected. Therefore, we can take the loop and use these diffeomorphisms to act on the space of symplectic forms of a given cohomology class. So the class comes from embedding of our surface into some projective space. Sorry, I have a question. So where did I use the assumption that the circle in diff was trivial? It was used to claim that W is smoothly trivial fiber bundle. It's equivalent. So this the loop we constructed is trivial if and only if the bundle W is smoothly trivial, and we need the triviality of W to apply the definition of family Seiberg-Witten invariance. So we define family Seiberg-Witten invariance for trivial bundles for families of metrics and perturbations. So okay, there is a generalization I would like to mention. So if we embed our surface into some projective space and equip it with an induced symplectic form, then we can look at the space of symplectic form and use our loop to act on the space of symplectic forms. And the claim is we get a non-contractible loop of symplectic forms. And the proof of this generalization is more or less the same as in the talk, but additionally we need to use some result of Taub's from his Seiberg-Witten equals Gromov-Witten works. That's it. Thanks a lot.
Lovely. We're getting some thumbs up. I'll leave it open. People can unmute and ask questions if they wish.
I'll try a question. Can you use a similar technique to do some higher homotopy groups for some of these complex surfaces? You know, in diff of some of those complex surfaces?
I don't know. No, I cannot. Well, probably you can.
Oh no, well, I don't know how. I mean, I'm not for those examples. I don't know how, but I just that was the point of the question. I mean, are there parameterized versions of these flops and so on?
Well, in principle, you can consider families over complex two-dimensional disks with singularity, and if you find some interesting resolutions, then probably yes, that would lead to some non-trivial elements. But so it's relies on some algebraic geometry I'm not familiar with, but I wouldn't be surprised to if such generalization exists.
And also maybe a technical point. In deriving the contradiction at the end, you know, you showed that there were curves when the general theory would say that the invariant should be 0, but then you've sort of demonstrated that in fact the invariant's not 0. So at some point, do you have to verify that those curves are, I mean, that those solutions of the Seiberg-Witten equations are in essentially, you know, in smooth parts of the moduli space, so that they actually are contributing, you know, with the correct sign?
Well, you mean that they're transversal, that they're stable?
Yeah.
Well, actually, they are stable because when you have a curve in a threefold, then the curve is rigid if the splitting of the normal bundle is O-1 times O-1, then this curve is rigid. And because of this, the Seiberg-Witten solution is also transversal. And but the proof of this transversality is done in Kronheimer's paper. So.
Oh, thanks.
I have a question.
Sure.
So I remember in your paper you mentioned that this construction of loops in diffeomorphism group is really some local construction. As long as you have some embedded sphere with certain condition, you can do a similar operation. Yeah, is that true?
Well, yes. The flop itself is done in a neighborhood of a rational curve. So.
Okay.
So everything is happening in the neighborhood of a rational curve. Now, if you have Sampho manifolds, not necessarily complex or symplectic and -2 curve, you can semi-locally in the neighborhood of this sphere put a complex structure and do everything. So the loop is defined for manifolds that has -2 sphere, but the proof works only for algebraic surfaces. The proof from the talk works only for algebraic surfaces.
So it doesn't work even for general symplectic manifold, does it? No.
Well, you need to use some additional techniques.
Okay.
Some kind of neck stretching or. I mean, the idea is everything is localized in a neighborhood of a -2 sphere, but to give a rigorous proof for it, you need you either do everything in algebraic category or use some analysis.
Mm.
Thanks.
And okay. And I have another question. So show that, okay, so did you show that this non-trivial element is non-trivial, or you can actually show that it's non-torsion? Is it infinite order or finite order if you just?
Well, in the talk we used mod 2 Seiberg-Witten invariance, so we didn't prove anything about the order, but yes, it is an element of infinite order.
Okay. And okay. Thanks. Well, since no one asked, may I ask another one question? Sorry. Yeah, you mentioned that this argument doesn't work for K3 surface. Could you explain a little why it doesn't? Why K3 surface doesn't work?
Well, how can I? So we define some family invariants. Family Seiberg-Witten invariance, and there is a general theorem, let's say a theorem or a consideration, that they vanish always except possibly when B plus equals 3. And K3 surface is exactly B plus equals 3 manifold. So that's why. And we need this vanishing result. So.
Well, this is some kind of, I mean, So I think what you say is that essentially when b plus equals 3, there could be something non-vanishing, right? Well, in principle, there could be non-trivial fact.
You still have the loop. You still can you can do the flop, so you can have some loop in the group of diffeomorphisms. It's just the proof that doesn't work.
Can you prove, but by this method, that that the loop this loop you constructed is different from the loop, say, coming from this hyper-Kähler family? In other words, to sort of essentially subtract one from the other.
Well, hyper-Kähler family is smoothly trivial. It doesn't give you any.
Well,
hyper-Kähler.
no. So, but you on your slide you wrote that there are none. When b plus is 3, there are these non-trivial families.
Yeah, non-trivial in the sense that they have non-trivial Seiberg-Witten invariants. The non-trivial family invariant.
Okay.
Not in the sense that the bundle is non-trivial. So the family invariants, the family invariants we use are defined for smoothly trivial bundles.
So I think in b plus equals 3 case, there are some word crossing phenomenon, right? I think that's similar to a single mathematical with b plus equal 1 case.
Come again?
So I mean, if b plus equals 3 case is somewhat similar to a single mathematical b plus equal 1 case. So there are some word crossings, and
it's exactly the word crossing. It's the wall crossing that gives you
side of the wall. I mean, there is a similar computation. If you can compute like which side of the wall is his, then it's the Seiberg-Witten invariant is actually some well-defined invariant, and you could possibly use that to say something interesting. Just like b plus equal 1 case for a single format.
Well, I probably KK3 has its own proof, not gauge theoretic. I'm still thinking that there might be a trick for K3.
Okay. Thank you.
Thank you.
It's rather late in Switzerland, so maybe I will say thank you to Gleb, and we'll post the recording and take it up again next week. Thanks, everybody.
Thanks.